The first half of the lecture is going to do largely the first 10% of the lecture has to do with cats. So let's see what we've seen so far. Pattern classification tasks like, does this picture contain a cat? Is the cat? Or does this recording include the word hello? We found are best performed by networks with scan. So scanning an input of the network and combining the outcomes is equivalent to scanning with individual neurons hierarchically and combining the lot. The first level neurons scan the input, the second level neurons scan the maps formed by the first layer neurons, and so on. We saw that we can redistribute this computation in different ways, and that deformations can be handled by max pooling or operations that are somewhat invariant to small, mild displacement of objects. So for two-dimensional or higher dimensional scans, the structure is called a connet. For one-dimensional scan along time, the structure was called a time-delayed neural network. So all this we saw. Now, where exactly did this crazy structure come from? It turns out that, the way we presented it in the last class, it was all very logical. You're looking for a particular pattern, you're going to scan it, right? That makes sense. But that's not where the model originally came from. The model's genesis comes from a completely different place. People have been trying to understand how humans and animals understand the visual world for a very long time. So, and for the longest time, nobody really understood it. What is the neural process through which we are able to comprehend the visual world around us? Pretty much everything that people did was kind of focused on behavioral studies. How do people respond to visual stimuli? So the most common examples of the kind of studies that people did are those pictures up there. You see the figure at the top left? What do you see? Anyone?
A cube.
A cube? How many of you see a cube? There is no cube, right? So it's just a bunch of circles. How many of you see the dog? There is no dog. So this is this business of gestalt. Folks, come up front. I have no mic. So where the brain has this tendency to just organize everything, all the stimuli it gets into something that's recognizable. And specifically, for instance, we have this field where we like to recognize faces. It turns out that babies recognize face-like objects or face-like patterns from the moment they are born. Which is why, we see ghosts, we see faces on the moon, we see face-like patterns where there are none, because we are heavily biased towards recognizing faces where you only have some kind of a pattern that might compose a partially obscure face. But then, continuing along the same trend, that panda, there's no panda, right? There is no sphere, the sphere doesn't have spikes. But you're seeing all of these because your brain is putting everything together. This is all people really understood about the visual process. And there wasn't a great deal of insight into how the brain actually worked until this beautiful paper by Hubel and Wiesel in 1959, which has to do with cats. Lots and lots of cats. This was the first study on neural correlation of vision. The paper was called The Receptive Fields of the Cat Striate Cortex. The striate cortex is a region at the back of the cat's brain. It turns out your brains, your eyes, they're all solid evidence that there's no God, right? It's completely inverted. Your eye, the first layer on your retina is the nerves. And the sensors are behind the nerves. So which means that the nerves have to go back, puncture a hole through your sensors, and then go back into the brain. Which means there's a blind spot in your eye, which is an intensely stupid design. If we were to design it, that's not how we design it, right? And then it doesn't just go and connect to the earliest regions of your brain, it goes all the way back to the very back and then connects to something at the back of your brain, which is also equally stupid. Anyway, so that region is the visual cortex. In the case of the cat, it's called the striated structure, and so it's called the striate cortex. And Hubel and Wiesel actually studied this on cats. They tried to understand how this striate cortex responds to visual stimuli. They cannot hold up 24 cats, anesthetized and immobilized them, put them on artificial respirators, pump them full of sodium pentothal, which is the truth serum, and stuck electrodes into their brain and conducted experiments on them. The paper very carefully doesn't mention whether the cats survived the experiment, but then afterwards they do say that the brain tissue was studied. So I leave the rest to your imagination. Now, this is what they did. The iris was kept open because now the cat is anesthetized, and they stuck electrodes on individual neurons in the visual cortex. And then they excited the retina with stimuli, light of different wavelengths in different patterns. So they would just scan the retina and see if when and how each neuron actually responded. And here's what they found. This was again 1959, right? So they found, for instance, that, say this is your retina. If you scan it, the retina would, the neuron would respond if there was light in these regions, but the response would go down if there was light in these regions. So you had inhibitory areas, and you had excitatory areas, and then you had areas of the retina where the neuron simply didn't care what was happening. So if you just beamed a light stimulus covering the entire retina, nothing happened. But then if you had very specific patterns, basically if you had a pattern which was oriented like so, and no light adjacent to it, so you're very specifically looking for linear patterns, then the neuron would excite. So you could either just incident this pattern of light, or simply take a single pulse and move it up and down. And if you moved it up and down in this region, then the neuron would fire, elsewhere it wouldn't fire, right? And so it turns out that the receptive field of the neuron, which is the pattern to which the neuron actually, of light to which the neuron actually responds, ends up largely being consisting of oriented kind of vertical, linear structures. So here are some figures from their paper. They have a little beam of light which they're moving back and forth, and you can see what happens to the response of the neuron as this beam of light rotates. When it's nearly horizontal, there's nothing. Then as it keeps rotating, when it becomes vertical, there's a whole lot of pulses being generated, but then as it continues to rotate, the pulses go away. This is regardless of whether you have a full beam or a full pattern, or you just have a beam which is going halfway across the, going from center to a border, right? The same pattern emerges. So the response, the neuron is sensitive in this particular case to vertical bands. More generally, the neuron is sensitive to bands of light. So oriented slits of light were the most effective stimuli for activating the striate cortex. And in a later paper, they actually sort of built on this and showed even more interesting stuff. They showed that within the cortex, there were two levels of processing. Something they called one level of processing was performed by something they called the S cells, or the simple cells. The second level was performed by something they called the C cells, or the complex cells. So the S cells and C cells behaved like so. The S cells were connected to a series of retinal cells, which were typically arranged in a linear manner. And so if you had all of these three retinal cells, now each retinal cell is actually responding to an entire circular pattern, or a nearly circular pattern. But the retinal cells themselves are arranged in a line. So if these three guys fire, then the S cell, which does something like an AND, actually fires. Right? But then the S cell tends to be not very robust. It will fire if there are random flashes of light, if there's noise, and so on. The next level, which is the C cell, actually looks at groups of S cells, and that fires only if a majority of the S cells fire. So it sort of cleans up the act that the S cells perform, act of the S cells. And so the overall structure has something like this. The complex C cells build up from similarly oriented, the complex C or complex cells. So there's a almost tautological terminology over here. Their patterns build up, their responses build up from those of similarly oriented simple cells or S cells. And they basically fine-tune the response of the simple cell. And then there's a build-up. The first level of cells respond to simple oriented patterns of light. The next level actually of S cells looks at the output of the C cells from the previous layer and builds on top of those. And then their responses are in turn cleaned up by another layer of C cells, and then you have another layer of S cells which look at the outputs of the preceding C cells and so on. So as you go through this simple complex structure, the patterns that the neurons respond to become more and more complex. And they actually continued this experiment. If you thought cats were bad, they actually continued experiments on waking macaque monkeys, which is kind of sad, so we won't go there. And just to add insult to injury, it turns out the studies were, how shall I say, best to cite their paper. This model cannot accommodate color, spatial frequency, and many other features to which neurons are tuned. The exact organization of all these cortical columns within V1 remains a hot topic of current research. There really wasn't any major conclusion to be drawn, except it did lead to the development of convolutional neural networks. So that's where we come in, right? So fast forward from 1959, 21 years to 1980, and Kunihiko Fukushima realized that he could computationalize this model, but there were deficiencies in the model. First and foremost, your visual response has shift invariance, right? It doesn't matter whether your grandmother's standing over here or if she is standing over here, you're going to recognize your grandmother. And this actually, I'm using the term grandmother because they actually speak of something called a grandmother cell. How many of you have heard of this? Have ever heard of the Jennifer neuron, Aniston neuron?
Oh, yes.
Yes, right, he knows from that. So there's several years ago, this was an interesting paper. It turns out that if you have epilepsy, then you're a great subject for neurophysicists. They take you into a hospital, they open up your skull, and they leave you there with your skull open for several days. Then along come these crackpots from the computer science and the neurobiology department, and they put little meshes on your exposed brain with wires coming out of it, and then show you lots of different things. This is not part of the epilepsy treatment. This is completely different. Right? They're just exploiting your open skull. And look at what you respond to. And it turns out that for one particular character, there was a neuron which only responded when he was shown pictures of Jennifer Aniston. So this was the famous Jennifer Aniston neuron. Now, nothing special about Jennifer Aniston. He probably had, and I'm not very good with actors and actresses. Name another actress, right? So he probably had one for whatever XYZ, one for Brad Pitt, and one for his wife. So it's just that we have very specific neurons which respond to very specific patterns, and somewhere in there is a neuron that responds to your grandmother's face. So we call this the grandmother cell in the literature. So your grandmother cell fires regardless of where your grandmother is in the picture, right? So Fukushima's model, computational model, had to account for this. Here is his computational model. He called this the neo-cognitron. Obviously, this must have been version 2 of his model because it's the neo-cognitron. There must have been a cognitron before this, I'm guessing. So the neo-cognitron had modeled the visual system as consisting of a hierarchy of modules, each comprising a layer of S cells followed by a layer of C cells. So within each group, you had a layer of S cells and C cells. You had several such groups, each which fed off the previous layer. Within each group, only the S cells were plastic, meaning they could be learned. Their responses could be learned. The C cells were fixed. Their only job was to clean up the act of the S cells. So S cells respond to the signals from the previous layer, and C cells confirm the S cells response. something is really wrong with my slides. The lower half of my slides has kind of gone away, and I'm just having, in addition to missing pointers, microphones, and such like, I'm also missing lines on my slides. So here's the model, right? Each simple complex module looks like this. Now, in the simple module, you had a layer of simple, what he called planes. Now, each plane over here consists of a detector for one specific pattern. So, for example, this guy over here might be looking for eyes, and if this is your retina, this location over here is looking for eyes over here, this over here is looking for eyes for the eye over here, this over here is looking for the eye over here. When you get out here, this pattern here is looking for the eye over here. So every one of the cells in that particular layer is looking for the same pattern, but in a different region of the input. So also, this might be looking for noses. So this over here is looking for a nose here, this is looking for a nose here, and so on. By the time you get to this bottom, that's looking for a nose here. Each of these planes is looking for a specific pattern. The plane consists of a number of cells, but since all of them are looking for the same pattern, just happen to be looking at different regions of the input, every one of those cells has exactly the same response. And what about the C cells? The C cells behind them, these planes, he organized them as rectangles. Now the C cells behind them is also organized as a rectangle. Each C cell over here was looking at a region of S cells and just sort of doing something, combining all of the information from these S cells to give you one combined response. So the C planes naturally were smaller than the S planes because they're looking at groups of S cells and they're sort of cleaning up the act, right? Now, in Fukushima's original paper, the S cells were looking at elliptical regions of their input, and the C cells in turn were looking at elliptical regions from the S planes, right? Now the output is going to be again a collection of, this is the S, there's going to be a collection of C planes, one for every S obviously, and then in the, so here's the complete network. You have a collection of S cells looking at the retina. You have a collection of C planes, each C plane looking at the corresponding S plane. But then at the next layer, when you look at the next layer of the S plane and the next layer, this is the S, each plane is looking for a pattern, a more complex pattern than what the previous plane looked at, and so it's trying to compose the pattern from the outputs of the previous plane. So this, for example, might be looking for something that includes two eyes and a nose. So if it's including two eyes and a nose, and it wants to find two eyes and a nose in this region, what it must do is look for the nose, the left eye here, the right eye here, and the nose over here, and put all three together to compose this more complex pattern. And so the first C plane in the second layer is going to be looking at the outputs of all of the first S plane in the second layer is going to be looking at the outputs of all of the C planes in the previous layer. And of course, every one of these guys is going to have, every one of these dots is going to have exactly the same response. They're just looking at different regions of the input. So this might be looking at these guys, right? And then corresponding to this, there would be a C plane which sort of cleans up the show. And you would have similar such pattern detectors. This might be looking for combinations of eyes and noses. The next one might be looking for a chin, what have you. So you have several of these planes. Each of them is following the same concept. And then these S planes in turn are composed of, followed by C planes which refine the output of the S plane. Now, the actual response of these neurons, Fukushima came up with a very complex formula. I would love to be able to explain this formula to you and how he derived it. But to be honest, after several readings of the paper, I still cannot. What I did realize is that the response he has for the S plane looks a whole lot like a ReLU, and the response he has for the C plane looks a whole lot like a max. So you can just replace the S plane with the ReLU and the response of the C planes with the max, and the whole thing still kind of works, right? So what happens here? The first layer only looks at the retina. Subsequent layers look at the outputs of the previous layers. As you go deeper, each layer is forming more and more complex patterns that it's looking for. And as the depth of the pattern, layer increases, the complexity of the pattern it's looking for keeps increasing. Now, this is a model, right? You want to learn it. How would you learn it? So here's what he did. Let's consider, say, this S-plane. Do I have an eraser here? I'm always missing things. Okay, let's draw this here. So let's say I have a collection of C-planes in the previous layer, and I'm going to be I'm trying to be composing, learning the responses for the S-planes in the subsequent layer. Now consider the output of any one C-plane over here. This is going to be contributing to the outputs of every S-plane in the subsequent layer, right? So he would look at which of these was the largest. Say this was the largest output and these things were less faint. Then he's going to attribute this one to this guy and not to the remaining planes. So he only attributes it to the one plane which has the highest response to that particular input. And then you just use a straight up Hebbian rule, which says, you remember the Hebbian rule? It was W plus some learning rate times xy, right? So it would be the product of these two guys. And this weight would be updated by that value. But then because all of these guys have the same response, the weights for every one of these other neurons in the plane are also going to be updated in the same manner. Now, that means that this plane has been updated, but then it turns out that if you look at different regions, different pixels in this plane are going to end up being attributed to different S-planes. So every S-plane is going to end up being updated. And similarly, every point in every plane in this layer is eventually going to end up contributing to the updates for every one of these layers above. Okay? So that was the entire learning process. So this is how he set it up. This is the figure is kind of explaining what I said. But what does it learn? As you go from the input to the output, the whole process is unsupervised. There is no supervision. All you do is randomly initialize the entire network, and then you present it with inputs. Now, you use this for the very first layer, you go and check, okay, which S-plane does this guy excite most? And then you just update this weight and then update the weights for all the neurons over here. Do the same thing for every pixel in the picture. You have managed to update the weights for all of the neurons and all the S-planes in the first layer. The C-plane doesn't have to be learned. Then you use those C-planes to update the weights for the S-planes in the next layer, and so on, right? So as you keep going deeper, you expect each S-plane to be looking at finding more and more complex patterns, and you would find that if you presented this model with lots of examples of characters, then of the character A, then the first layer of S-planes may end up learning different components of the character A. The next layer may end up putting these things together to actually compose the character A, and so on. So, and this is the winner take all strategy. So the whole thing ends up being somewhat robust to distortion. And since the whole thing is unsupervised, it's effectively just clustering. And so here's what they actually found. Fukushima showed that if you just presented lots and lots of examples of characters to this model, mind you, there is no supervision. The whole thing is just unsupervised, right? You find out that in the final layer, the different planes end up actually just capturing the different digits. So you could present it lots of examples of zeros, ones, twos, threes, and fours. You might find that in the third layer, that particular neuron fires only if the input is a 0 and not otherwise. A different neuron might fire only if the input is a 1 and not otherwise, and so on. And this is regardless of the noise. So it has actually learned naturally about the kinds of patterns that occur in the visual stimuli that have been provided, and it has learned to cluster them and form sometimes semantic groups. It could learn characters, it could learn digits and whatnot. So this is beautiful, right? And you already see how this is beginning to look like the convolutional neural network. What is the difference? There is no supervision. Now, once this model is proposed, the obvious next step is, why let this model just learn whatever it learns? Why not tell it what it must learn, right? So that means there needs just one little addition. You add supervision. The neo-cognitron is fully unsupervised. The semantic assignments are automatically learned. So can we add supervision? It turns out there were several people who attempted this. There was temporal correlation by Hamartless and Marx. This was in '88. Out here in CMU, Kevin Lang's PhD thesis introduced supervision, and he called the model the time delay neural network. It won several awards. And at about the same time, Jan LeCun added supervision, except instead of doing it for speech, he did it for images. But they were all pretty much doing the same thing. And the real innovation in this was that one final bit, which is adding that final output, which takes the combination of everything that comes in and outputs the max or the softmax, right? This is what we've seen when we are scanning for patterns and producing the output. And once you do this, now you can say, here's what, in this image, I see the character A. I want it to be the A, compute the data difference, backpropagate, and learn the pattern, learn the responses for every, learn the weights for the entire network. And that's all you really have to do, right? So, and you would only be training the S cells, you wouldn't actually be training the C cells. Now, when you actually begin implementing this, remember this. In the original neo-cognitron, when I formed an S-plane, you didn't have just one neuron, you had many copies of the same neuron. If I updated one, I updated everything, right? You don't need many copies of the same neuron. You can just have one copy scanning, and it's exactly the same behavior. We saw this in the last class. And so here are the minor modifications that they added. They assumed that the receptive fields were square rather than elliptical, as the neo-cognitron originally had. And so the receptive field of every S cell was square, and the receptive field for every C cell was also square. And the actual response looks like so, right? So if you look at this, if say this is the output of a C cell, of a set of C cells, this is S. Now this guy is going to be looking at the square receptive fields, the square patterns from every one of the previous planes, right? So you really want to be summing over all of the planes. Within each plane, it's got a collection of weights, and you're superimposing the weights in the corresponding region of the image, and you're computing an inner product and summing over the lot. So here are the weights, and observe that these weights are position independent. So meaning that if you consider the response here, the weights with which this would look at this guy are going to be the same as the weights with which this would look at this guy. So the weights don't change based on which portion of the image you're actually analyzing, right? So you have the weights, and then you have the corresponding region of the image. You're just imposing the weights on top of the image. You're computing a pixel by pixel pairwise product. You're summing the lot. You're summing this over all the planes, and that's going to give you one combined response at one particular point, and that's put through an activation, which is the sigmoid, and that would be the output out here. That's going to be the S cell output. And then the C cell, it just looks at a rectangular patch of the S cells and picks up the max, right? So this is the very simple response that they actually have. Now observe that instead of having many copies of the neuron looking at every region of the image, you can have just one neuron scanning. And we know that scanning with a neuron is the operation that we called, what did we call it in the last class? Convolution, right? So this becomes a convolutional neural network. And so here was the piece of code that actually won the Turing Award, right? This was the LayNet back from the early 90s. And you can see that how it responds to characters as it slides through the visual field. And as soon as the character comes to the center of the visual field, it correctly recognizes it. This was a pretty revolutionary thing back then, and this was actually used by the US Postal Services for a long time. This is Jan LeCun's LayNet, where I think the Lay stands for LeCun, but I may be wrong. Now, questions, anyone? So here's the story so far. The mammalian visual cortex consists of S cells, which capture oriented visual patterns, and C cells, which perform a majority vote over the S cell outputs. The neo-cognitron, which is a computational model proposed by Fukushima, emulates this behavior with planar banks of S cells and C cells, where only the S cells are learned and respond to patterns in the outputs of the previous layer, and the C cells, once again, just perform the equivalent of a max over groups of S cells. Unsupervised learning within this model actually ends up learning useful patterns. LeCun's LayNet added external supervision to the neo-cognitron, and here the S planes of cells with identical response were modeled with a scan, a convolution, and the C planes are emulated by cells that perform a max over groups of S cells, which reduce the size of the S plane. And this gave us the convolutional neural network. So everything that we spoke of in the last class, it didn't actually arrive. It was not originally actually arrived from the perspective that we presented it from in the last class. It started off as a computational model for a biological model for study based on studies that were done on cats, which is why this class is all about cats. Now, so here's the general architecture of the neural network. The convolutional neural network comprises, so I can't see what's in the last line, neither can you, so we are both in the same state. I'm going to make it up. If it sounds wrong, just let me know. Now, so the convolutional neural network comprises a sequence of convolutional and downsampling layers. Convolution layers comprise neurons that scan the input for patterns, and downsampling layers perform max operations on groups of outputs from the convolutional layers. The two may occur in sequence, so you could have convolution downsample, or any other pattern, right? You could have convolution downsample. It doesn't make sense to have downsample followed by downsample because it's basically one large downsample operation. So and we're calling it downsample because when you pick a max and then you move on, you're reducing the size of the map. So, and from each region you're picking one, so you're downsampling each region down to one value. So the whole thing is called a downsampling layer. Then when you get to the final downsampling layer, you have a whole bunch of neurons, neuron outputs, and each of these outputs is looking for a pattern anywhere in the network, right? So just as we saw in the last class, that entire collection can now be put through a softmax or a max or an entire multi-layer perceptron to actually get the final output. So the end consists of an MLP which is operating on what we call a flattened version of the outputs of the final layer of neurons. So here only the convolution layers are learnable. Their parameters must be learned from training data for the target classification task, which could be digit recognition or face recognition or what have you. The downsampling layers, of course, have no learnable parameters, right? So what does the convolution layer do? It does three things, of which you can see two. Now, it's the convolution layer actually consists of a series of maps corresponding to the S planes in the neo-cognitron. And these can be called feature maps or activation maps, just terminology. So I will also be just sort of flipping back and forth between the terminology, these two terms. Now within each map, right, if you consider what happens at any one location, there's actually a pair of operations that happens. So if I consider what happens out here when this guy is, where did I put the eraser? I didn't. Right. So consider what happens when this guy is looking for a pattern in the top left corner. It's actually looking at all of these inputs, right? Now, what it does in the process is twofold. First, it computes an affine combination of all of these guys, all the pixels here, all the values here, and all the values here. It computes an affine combination of the lot. And this affine combination is actually the pattern that's used to compute the affine combination scans the input. So this pattern of weights is called a filter. It's called a learnable filter. So the first step is the computation of the affine combination, which we call the convolution. But once you compute the affine combination, you actually apply a activation to the affine combination. So this is a two-step process. The convolution itself is the computation of the affine combination, but the output further puts this affine combination through a activation. That's just like in any standard MLP, right? And if you want to compute the affine combination at any one location, you're actually going to be looking at all of the maps from the previous layer, as I just showed in this figure, right? Now, let's consider what happens in a particular map, a single map, right? So what do I mean by a convolution, just in case you didn't get it? So again, I'm looking exactly at what happens just in this one map. So I'm trying to compute the output for the convolution layer, right? And so I'm going to see what happens here. How does the location that all of the arrows point to respond to the specific map which is circled in the circled by the brown patch? So I'm looking at how the brown patch contributes to one point in the corresponding map. So I'm not looking at all of the maps, I'm looking at only one map, one patch, okay? So in that case, corresponding to that brown patch, you would have a filter. So if I'm looking for 3x3 regions, looking at 3x3 regions in the map, my filter is going to include how many numbers? 10, right? Actually, well, the 10th can be thought of as shared, because when I'm looking at an affine combination, there are two sets of things. One is the weights, and the next is the bias. Don't forget the bias, never forget the bias, right? So the filter is going to have those 9 values, which are shown in my example. All of the weights are binary, they're either 1 or 0. And the image, the map from the previous layer, is illustrated by this patch in green, which is going to again be a bunch of numbers. And you would just put the filter on top of this patch, like say at the top left corner. So the filter values are shown in red, and the underlying map values are shown, in black in the figure to the center. And you would be multiplying the map value and the filter value at each location. So there'd be 9 such multiplies, and then you sum the lot, and then that final sum is going to also be added to the bias. So the output over here is going to be 1 times 1 plus 1 times 0 plus 1 times 1 plus 0 times 0 plus 1 times 1 plus 1 times 0 plus 0 plus 0 plus 1. So that is going to be 1, 2, 3, 4, and the bias is 0, so the sum is 4, right? And now you'd perform this at this one location, and then subsequently you're going to sort of keep computing that operation as you go left to right, scanning the input, right? This what is happening here must be very clear. Now this is just showing you what happens for one map. In reality, and of course, you don't have to be scanning with a stride of one step. So you could be moving forward 2 steps at a time. So you could be doing something like this here, and then jump forward 2 steps, come back here. You're going down also by 2 steps now, right? Observe that, and when I went down by 2 steps and then jumped forward by 2 steps. And this means that the resulting output map is going to be smaller in size, right? But now let's look at what really happens. When I'm trying to compute that one map, you see that little gray patch, little gray square to the in the patch to the right. That thing is actually being computed from every one of the maps in the previous layer, right? So if it's looking at 3 cross 3 patterns, it's going to have a 3 cross 3 pattern for every one of the maps in the previous layer. So you'd have a total of 9 weights, right? Plus 1, which is the bias. And so the weights are shown by this color-coded set of squares. And so the actual computation you're going to do is going to be something like that. You're actually using all 3. These 9 squares are scanning through their corresponding maps simultaneously. And you're adding the lot and you're also adding the bias, right? And each map, so this would be just for the first map. If you were trying to do this for the second map would be doing the same thing, except now the weights for the second map are very different from the weights for the first map, right? It still has 9 weights, but the values are all different, as I've tried to illustrate using the different color coding. And you'd be scanning using these guys rather than the original, which is very specific to this particular pattern. Now the whole thing, trying to visualize this as 3 different things going on, moving simultaneously, is maybe a little bit tedious, right? So for purposes of illustration, it's more convenient to actually think of those various planes that I showed, one below the other, as being stacked one behind the other. So instead of having a number of planes, I can think of this as a cube consisting of several planes, right? And now my filter is going to also be this little cuboid, where the cross section of the cuboid is square, but the depth of the cuboid is as many planes as I have in the previous layer, right? And so when I actually perform my computation, here's what I'm going to do. I would put this filter, which is a cuboid, in the top left corner of the entire structure, and I'd be doing a pixel by pixel product and summing the lot and then adding the bias. That's going to give me that one value out there. So observe what's happening here. This guy, which I have shown with the curly brace, that is showing you the computation for one plane. Just that yellow patch. You're scanning over that entire yellow patch. You're going over the entire yellow patch and doing a pixel by pixel product and summing over the lot, right? And that patch is going to have its own set of weights, this guy. So this weight, observe, it's very specific to the plane P, to the layer, right? And I would actually be doing this computation simultaneously for every patch. So the overall summation is going over all of the patches, right? All of the planes. So this is the actual summation that you're performing. Again, keeping in mind that the filter, which was this cube, has different values at every single location. So it's not as if the weights in one plane are identical to the weights for any other plane. They're all different. I have this cuboid of all different values, which I've put on this stack of planes. I'm doing a pixel-wise product and summing the lot and adding the bias. And that cuboid is scanning the input to compute the entire map, right? So if I were to write pseudocode for this, and now the pseudocode on the slides is actually been verified by my wonderful TAs who implemented every line of code over here and made sure that it's all right, including the indices and the values. So if you have any doubts about the incorrectness of the indices, then you're wrong. So here's what you're doing. For each layer, for each neuron, now when I speak of one neuron or one filter, right, that neuron is scanning, that corresponds to one S-plane. It's simultaneously scanning all of the planes in the previous layer, right? So each neuron now corresponds to a cube, right? So you're going to cuboid. So you're going through the layers. For each layer, you'll be going over all of the neurons. And this segment is pulling out a cuboidal location from the stack of planes at a specific location. And then you just compute an inner product between this, what I call the segment, and your cuboidal filter itself. And that's going to give you the output affine value at that corresponding location Z. So this is the just the affine operation. Now, the result of again, keep in mind that the result, the stride of the convolution doesn't have to be 1 pixel. You can actually be sliding forward more than 1 pixel at a time. So the size of the output depends on various factors. It could depend on whether you're striding by 1 or not, but there are other issues that also come in. So let's take a look at these for completeness sake. Now consider this guy here. I'm scanning this 5x5 image using a filter which is 3x3. How many steps can I take before the filter falls off the edge? Stride 1. 3, right? Once I go take a third step, if I try to take a fourth step, the filter falls off the edge. So what is the size of the output going to be? Only 3x3, because there are only so many positions I can move before my filter falls off the edge. Now suppose I were using a stride of 2. What is the output going to be? There are 5. The filter is 3x3. After one step, I have covered the 5. Then if I try to move ahead, my filter begins to fall off the edge. So now the output is going to be 2x2, right? So in general, if I have an image which is size n cross n, right? This is n cross n, and a filter which is, say, let me call this k cross k. What is the size of the output going to be? So what I can do is I can put this k cross k over here, so I get at least one output. Whatever I do is going to be 1. The remaining is going to be n minus k, right? So it's going to be plus n minus k, and I'm striding with a stride s. I will need a floor because these are integer indices, right? So that's the number of pixels I'm going to have in the output in each dimension. And so, well, I just sort of gave you the answer. For a general scan of an image with n, with a filter of width m, with a stride of size s, the actual output size is going to be n minus s, or n minus m over s plus 1, right? So assuming you're not allowed to go over the edge. Now this happens, one outcome of this is that the output ends up being smaller than the input, even if you're using a stride of 1. In many situations, you don't want the output to be smaller than the input. You want to actually maintain the size because you want to keep track of proportions. So when you want to maintain the size to keep track of proportions, then what we will do is to allow the filter to fall off the edge. But if you're going to allow the filter to fall off the edge, it's not fair to do it in just one direction. You want to do it in both directions, right? So assume that I have a stride of 1, then how many rows did I lose when I was going from left to right? Over here. N minus m, right? Because I still have. So I'm getting n minus m plus 1. So this is how many I'm losing. The n goes away. I'm going to lose m minus 1 rows, right? So I would take m minus 1 over 2, and I would pad these many columns of zeros to the left and these many columns of zeros to the right. So once I pad everything with zeros, then the result is going to be the same size as the input itself, right? And so this is a common enough thing to be doing. What we will do is pad zeros all around, like so that the result is the same size as the input. And now regardless of the stride, the output is going to be in proportion to the in size to the input. So this is a common thing to be doing. Anyway, so the convolution operation actually results in a convolutional map, and now an activation is applied to every entry in the map. And in your homeworks, the activation you apply is the ReLU, as you've observed. So that's the overall, that's the complete pseudocode for the CNN. You have the affine combination Z, and then the actual Y is obtained by applying an activation to the Z, right? Now, that was just the convolution operation. The other operation that we have is the downsampling operation, right? So the downsampling operation, which we also call pooling, intermittently follows the convolution. And here's what happens. So let's say you have this map. We saw this in the last class. The downsampling operation is going to be looking at groups of pixels from the output map. And you're going to have one downsampling corresponding to every output map. So it's convenient to think of saying I have one C corresponding to every S, right? And the C is looking at only one S. It's not looking across all S's. And so it would be looking at, say here, this 2 cross 2 group, which might be 3, 1, 4, 6, and picking the maximum value, which is 6. And so that's what you'd be doing as you went left to right. At each location, you'd just be picking the maximum from that one location. So once again, the max may stride by more than one pixel. So you could be doing, this is, if you're going to be doing a max, it makes a lot more sense to be striding by more than one pixel because you're actually trying to account for jitter in the patterns, right? And so when you actually look at an n cross n picture and you compress it by a p cross p max pooling map, which strides by the width of the map itself, then which strides with some skip d, stride d, then the output, the size of the output is also going to follow just the same formula. Except here you may want to account for the boundaries in a different way, right? Use a ceiling. So you get the idea. Now there's an alternative. What is the purpose of the max? The purpose of the max is to ensure that you have some jitter and variance, right? So if the location of my petal moves a little bit, I should still detect the petal. I shouldn't be looking for it in a specific location. Now the max is one operation, but there are other alternatives, right? You could be looking at the mean of all four, and that might actually make more sense in some scenarios. So you could, instead of picking the max, you could pick the mean. Or you could even put them through a softmax, right? Or you can put them through some kind of a p-norm. Or you can even replace this entire max operation with a learned network which figures out how to combine all the pixels in that value to give you a best guess for whether the specific pattern occurred or not. These are all different variants on the simple basic max, and the whole thing, as a story, it doesn't break down. It remains the same story, right? And maybe the simplest thing to do is to not bother with this whole business of pooling. Remember that when you're striding by 2, you're reducing the size of the map anyways, right? You can hope that just by adding more convolutional layers with a larger stride, you learn some measure of position invariance. Now remember that if I were using a softmax instead of a max, that's exactly the same as just using a standard neuron, right? In which case it just becomes just a standard convolution with a different stride. So the latest architectures will just get rid of this entire business of maps, maxes, means, and other operations, which you remember were not motivated by, so much by logic as by the biological principles that we began with. But then we don't need to stick with biology. Computational models can actually be better. So these days we just use convolutions all the way through. And so that would, if you don't use these pooling layers and you just perform convolutions all the way through, where you use larger strides to reduce the size of the map, then you'd call this an all convolution network. And the pseudocode that we saw earlier is actually that for an all convolution network, which doesn't actually have the pooling layers. So here's the story so far. The convolutional neural network is a supervised version of a computational model of mammalian vision. It includes convolutional layers comprising learned filters that scan the outputs of the previous layer, and downsampling layers that vote over groups of outputs from the convolution layer. Convolution can change the size of the output. These may be controlled by zero padding. Downsampling layers may perform max P norms or be learned downsampling networks, or you can just do this entire downsampling by just using regular convolutions with a stride greater than 1. So questions, anybody? Before I continue? What's the time?
It's almost time.
Almost time? Okay. So let's put everything together. Can you just have the clock out? Since actually it's telling me the time at the top. Beautiful, right? Sometimes when things go wrong, they can also go right. So let's say I want to operate on images, and I'm looking for, maybe I'm analyzing these images to decide if they contain a house. Now a typical image is an RGB, right? So you have I'm going to assume it's color. It could be black and white, in which case it will just be grayscale. So this image is actually going to consist of those 3 images to the right. What I would do, so that's the input is 3 images. The first thing I do is to stack them up. Again, remember, instead of thinking of them as 3 independent planes, it's more convenient to stack them up one behind the other, right? And think of this as a cube, like so. And then typically, I mean, these days things that the computational infrastructures have become a little more flexible and more powerful. But for computational purposes, we like to work on square images. So you can keep track of things. And if you have, because if your network's looking at inputs that are too large, then you run into computational issues, and the number of parameters you'll need will also end up becoming too large. So typically you'd scale your input down to something like, say, 128 cross 128, or maybe even as small as 32 cross 32, which is what the initial ImageNet models looked at. And you'd operate on the rescaled images. It all depends on how you scale. It depends on what you can fit into your GPU. Chris, can you put the URL up?
Yeah, do I send it to you?
Just write it on the board. Yeah. And I will keep talking while they. Oh, just put it there. So this is the roll call. You can sign up, but I'm going to keep talking because otherwise I'll run out of time, right? So here's what we have. An input has 3 pictures. And you're going to have, for the first layer, some K1 filters. Each filter will be looking at some L cross L region of the image. So the actual number of parameters is going to be L cross 3 per filter. And the number of filters typically is going to be some power of 2. And the L cross L, the filter sizes are going to be 5 cross 5, 3 cross 3, or even 1 cross 1. So they must be small enough to capture fine features, particularly for scaled down images. But then there's this crazy thing. What is a 1 cross 1 filter? It's not really looking for a pattern, right? A 1 cross 1 filter, it just turns out, is just a simple MLP, which is looking at 1 pixel location through the depth, right? It's just a single perceptron, not even an MLP. It's just a single perceptron which is looking at 1 pixel through the depth. So a better way to represent these filters is to say 5 cross 5 cross 3, where I'm putting the cross 3 in parentheses to indicate the depth, but it's in parentheses because that's a direction you're not scanning in. You're only scanning across the x and y. There's no scanning along the depth, right? And so the output of this, so the parameters you'd want to choose are going to be how many filters, how wide are the filters, and what is the stride. And the total number of parameters is going to be, in this case, L squared, which is per color, times 3, plus the 1, which is the bias. And you have K1 of these filters. It's going to be K1 times 3L squared plus 1, right? So the stride is not a parameter you're choosing. Stride is not a parameter that's part of the model. The stride is a design choice, right? So you can also zero pad the input depending on whether you want the size to change, size to remain proportional or not. Yes.
So the 3 comes from, just to clarify, like number of like
3 colors,
okay, 3 colors.
right? You're going through. So what is the actual operation you're performing? These are exactly these equations are exactly the same that we saw earlier. I have this filter W, which is going to be L cross L times 3, right? So the indices are color, X position, and Y position. And I'm placing this position at different locations on the image and summing over the lot. So that's going to be my affine combination Z. And then there's the activation function that operates on it to give you the Y, right? So again, the filters are 3 dimensions. Now, all of these parameters need to be learned. K1 times 3L squared plus 1 parameters. They must all be learned as part of your training, right? Now, once you're done computing these y's, the next step is going to be pooling, if you so desire. And so the next step is going to be a pooling operation where for each map, you're going to be looking at a region and picking the max with this region. So this operation is going to be the max over the input, right, over this region. And this is going to be computed at each location. Now, this too can be thought of as scanning, right? And the parameters to choose are going to be the size of the pooling block and the pooling stride. You may also want to choose whether you want to perform max pooling, mean pooling, or any other kind of pooling. Now, specifically, if you're performing max pooling, then there's an important implementational step, and this has to do with computing derivatives, which we will look at in the next class, which is to say that you don't just say y, the output equals max of I. You're going to say the position is argmax P of IP, right? You're going to find the position and say this guy here has the largest value as the first step. And then the second step, you're going to say output is going to be I of this position. So you do it in a 2-step process. You keep track of where you picked up the maximum from. And then you read the maximum value from that location. You're going to need this when you actually compute the derivatives going backwards. So you don't just pick the max. You find the location of the max and store that, and then read the value of the max from that location. Okay? And that output is going to give you a collection of maps. And the number of maps you get is going to be K1 again, which you can stack because you had K1 filters, right? The next layer is going to be a bunch of, now these filters are also often called kernels, and the outputs are often called channels. These are terminologies you might have encountered. So when you think of a kernel, the kernel is just that cuboidal filter which is scanning the input, and the number of filters is the number of channels. I'm not really sure where this terminology came from, but that's what people use. So you must be familiar with it. I just use random terminology, so you're going to have to get used to that. Now, the next layer, I'm going to have, so what is the size of the filter for the next layer? Again, each filter is going to be looking at some L cross L region. But then what will the depth be? How many such regions do I have? K1, because I have K1 maps from the previous layer, right? So the next layer, the filter values are going to be, each filter is going to have K1 times L cross L parameters. And I would have some K2 of these guys, right? So the total number of parameters is going to be K2 times K1 times L plus 1, right? That makes sense to everyone, right? Mansi, you look puzzled? No, okay. So, and so the number of parameters to choose are going to be K2, the width of the filters, and the stride. The size of the filters is going to be L2 cross L2 times K1 plus bias, right? And so the total number of parameters is going to be K2 times K1 L2 squared plus 1. Okay? That output is going to give you a K2 maps. Then you'd do a downsampling on that again, and you'd get the reduced size of K2 maps. Then you'd perform the next set of convolutions. And again, when you do this, once again, you have to choose the size of your pooling and the stride. And you'd have to do this for every single layer. Each of these are design choices. And then you can continue doing this for as many layers as you want. And then in the end, whatever remains, you could just put this through an MLP. And design choices, again, is how many layers does my MLP have, how many neurons, and how do they combine. You can just have one softmax. The latest architectures don't actually use an entire MLP at the end. They just use one softmax. Yes, Michael?
Is the convention to add the bias once per cuboid or once per...
It doesn't matter, right? It's like summing all of the biases. So that would just be an unnecessary computation. It's once per cuboid, right? If you have once per plane, it's just a constant. You might as well just sum them all. Yeah?
The maxes, is that plane-wise or cuboid?
Plane-wise. The max is plane-wise, right? Every S plane gets a C plane, right? The max is plane-wise. So the max is plane-wise, but the convolution is a cuboid. So now each convolution layer maintains the size of the image with appropriate zero padding, and if performed without zero padding, it's going to decrease the size of the output. Now each convolution layer may increase the number of maps, right? Why? If I start off with K1 maps, I may actually have and I use K2 filters. It's like using K2 neurons, right, in the next layer. The number of neurons in the next layer can be more than the number of neurons in the current layer. And so the number of channels can actually increase at each point. Now, so each convolution layer may increase the number of maps from the previous layer. Each pooling layer with a hop of D is going to decrease the size of your maps. And within any particular layer, the filters are typically all the same size, but the filter sizes may change with the layer, right? Basically, all of the cuboids within any particular layer are typically going to be the same size, but when you go to the next layer, the cuboids may have different dimensions. So L1 doesn't need to be the same as L2. Okay?
Professor, just to confirm that hop there is the stride for the pooling layer.
Yeah. Okay. It could have a stride stride greater than 1 even for convolution. So if you didn't have pooling, you just get rid of that. You just get rid of the pooling layers and just have a larger stride for convolutions. Now, in general, the number of convolutional filters increases with the number of layers, because as you go through the layers, your maps get smaller and smaller. To retain the information, you want more and more of them. Otherwise, you're going to have a loss of information, right? Remember that if your original image has, say, 3 colors and 1024 cross 1024 pixels, then there are a total of how many independent values? 3 million values, right? So if you want to retain all of the information about the image as you go through, the number of channels times the output map of each channel has to be 3 million. Otherwise, you're beginning to lose information, right? I mean, you could make it smaller than that, but if you want to retain most of the information in the input, the total number of values at the output of each layer must not decrease too much from the size of the input itself, right? Otherwise, you're beginning to lose information. Now, mind you, losing information is not a bad thing, because the stuff you lose might be noise. But in general, it's kind of nice to retain as much as you possibly can to forward on to the next layer, as we saw even in lecture 2, because that allows subsequent layers to actually capture additional patterns, right? So this naturally means that as you go through the layers, the maps become smaller in size, but the number of maps is going to have to increase. So the number of filters will increase with the layer. Now, the various parameters you'd have to choose from now as a result is the number of convolutional layers, the number of downsampling layers, how they are arranged, how many convolutions followed by how much downsampling, the number of filters in each layer, the size of the filters in each layer, and the stride. Now, for each downsampling pooling layer, Again, you have, that's for the convolution layer. For the downsampling or pooling layer, you're going to have to choose the size of the filters, the stride, and actually the operation, whether you're going to be doing a max, a mean, or something else. Okay? And then the final MLP, you're going to have to choose the number of layers, the number of neurons in each layer, how they connect, etc. Again, in the latest architectures, you don't really have a full MLP towards the end. You just add more convolution layers and then finally just have a softmax. And turns out it works just fine, right? And in fact, so this sort of regresses to what we spoke about early in the last class, right? You're scanning for the input, scanning for the pattern, and then just doing a softmax over the outputs at each position. Turns out that's a pretty universal model. So this was the actual model that Jan LeCun used for his digit classification task. The inputs were 32 cross 32 images. The first layer convolved with four 5 cross 5 filters, which gave you 4 maps. And because he was not zero padding, the size goes down to 28 cross 28. Then he downsampled down using 2 cross 2 subsampling. So you still get 4 maps, but now the size is 14 cross 14. And then subsequently he had a 5 cross 5 filters convolving over it. So 14 cross 14 is going to become 10 cross 10, right? But then he had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I believe, 12 filters scanning over this. So you get 12 filters, each producing a 10 cross 10 output. And then again, a 2 cross 2 downsampling yet again to make it smaller. Then all of these values were flattened into one big vector, which went into a multi-layer perceptron with, I forget exactly what the architecture was, which gave you the final digit classification. And you saw the output. It worked quite well. Now, here's the issue. So we've seen what it looks like. We've seen how you've got to compute it. You've seen how many parameters it has. You've seen the different ways of arranging the entire computation. But then there's the final piece. How do you learn it, right? How do you train the model? Training is just like in a standard MLP. But remember, it looks very complex. But if you go back to the last class, what are we actually doing? It's just one giant MLP, right? You're just reordering the computation. You have shared parameters, but it's just one giant MLP. So that means that you really will not be, the training is going to be exactly what you would do for an MLP. You're going to have, the only difference is in the structure of the network. You'd be given training examples, images and the class. So if you were doing digit recognition, you'd be given images of digits and the digit they represent. You would define a divergence between the output of the network and the actual label. So if you were doing a classification task, this divergence is most likely going to be a cross entropy loss or a Kullback-Leibler divergence, right? And then you would use gradient descent, back propagating through the network, and the gradients are going to be computed using back propagation. We will be going through this entire business in the next class, but really at this point, you know enough to figure out all the rules yourself, right? The fact that it's a convolution that doesn't change anything. Eventually, it's just one large network scanning the input. And you could write your code quite blindly without thinking too hard about it, keeping in mind that when you have networks with shared parameters, you just pool the derivatives, right? You sum up the derivatives, and the whole thing should still work. So you would, so the things you would have to learn are the parameters of all of these, all of the parameters indicated on the screen. You'd start off from the output, and the back propagation, you could just use back propagation starting, you'd define the divergence between the output and what you want. The divergence, of course, is going to be maybe a cross entropy loss or a Kullback-Leibler divergence. That is going to be for one input. As always, training is going to be averaging the divergence over the entire training instance, training data, right? So the loss is going to be the average divergence over the entire training data. The derivatives are going to be the derivatives of this loss, which means that It's going to be the derivatives of the average divergence over the entire training data. You'll be computing the derivative of this divergence with respect to every single parameter in your network, and use just standard gradient descent to update your parameters. The key piece here is how you compute this derivative, and this again is exactly what we did earlier. The total loss is the average of the divergences across the entire training set. So the derivative is the average of the derivative of the divergences for the individual training instances with respect to the parameters, right? And that is what you really would be computing using backprop. So if you perform backprop, you would start off with the final layer. You'd use conventional backprop that we use for multi-layer perceptrons to propagate your derivatives through the network while updating the parameters of the MLP. And eventually, when you get to the input of this flattened network, you're going to have derivatives with respect to the input of the flattened network, which is the output of the convolutional layers, right? And then you can use those. And remember, again, this is important. The first flat layer is only the unrolling of the maps from the final convolution layer, right? And subsequent to that, you're going to pass the derivatives back through the convolution layers. Now, again, you could write all of the derivative rules blind at this point, but then if you want to be a little more efficient and if you wanted to sort of follow the principles of convolution that we've been using, we're going to have to make some adjustments. Particularly if you're using a max pooling layer, then the derivative computation will have to use the derivative rules we used for max activations, which we saw several classes ago. And we'll see this in detail in the next class, right? So exactly how we do the backprop, we're going to do this in the next class, but then what we've seen so far is that if you follow these rules, you're going to have the derivative with respect to every intermediate in output and every free parameter, which is filter weights and biases. And now these can be embedded into a gradient descent update rule, gradient descent framework to learn the parameters of the entire network. So here's the story so far. I'll stop here. The convolutional neural network is a supervised version of a computational model of mammalian vision. It includes convolutional layers comprising learned filters that can scan the outputs of the previous layer, and downsampling layers that operate over groups of outputs from the convolutional layers to reduce not the network, but the size of the map. The parameters of the network can be learned through regular backpropagation, and we'll see how we do that in the